Hello and welcome to my first video blog post in which I will discuss how to discuss the accuracy of surgical navigation systems. Here are some of the questions clinicians have in mind when considering accuracy. Basically, it comes down to having a number that they understand and that they could use to reliably assess and compare alternatives. Unfortunately, although surgical navigation systems have been around for about 25 years, clinicians don't get very good answers. Somewhat confusingly, when we quantify accuracy, we actually talk about the opposite of accuracy, which is the geometrical deviation between what we want and what we get. That deviation is either a distance or an angle, and the lower the number, the higher the accuracy, and vice versa. Let's look at how the results of accuracy studies are being reported in the literature. The examples I'm showing here relate to placing dental implants, and the deviations being measured are between where the implants was planned and where it ended up. In this table, there are two statistical deviation values, mean and standard deviation. They are reported for each of 7 different deviation types. When we try to compare the accuracy obtained by 2 navigation-assisted surgeons shown here, we can become easily confused. For example, if you look at the 4 numbers highlighted in yellow, we see that surgeon 2 had the lower mean angular deviation and surgeon 1 had the lower mean global platform deviation. Here is another table from another paper, this one being a meta-analysis of other accuracy papers. The table compares results for just one type of deviation, angular, and there are other such tables for other types. For each type of deviation, 6 statistical measurements are provided. Most of these were not actually reported in the paper being referenced. They were derived from the mean and standard deviation values reported on the assumption that the measurements are normally distributed. The assumption that the deviations are normally distributed pervades the field, and practically all papers that I've seen implicitly assume this distribution and report on it accordingly using statistical tools designed for normal distributions. Here's a quick reminder of what a normal distribution, which is also called Gaussian or bell curve distribution, looks like. The peak is also the mean and the median, and since the shape is well known, reporting only the mean and standard deviation is enough to tell us everything we may ever want to know about the distribution. It is surprisingly easy to see that deviations cannot possibly be normally distributed. If we try to plot the distributions for one of the distance deviation types reported for an accuracy study, we have a tail on the left that extends below 0, and there is no such thing as a negative distance between 2 points. We might think next that all we need to do is to take the absolute value of the deviations, so the negative values on the left of the 0 line will fold over to the right side, and we'll get a distribution looking like the black line here. But we'd be wrong. Think of bins in a histogram, each counting the number of deviation samples that fall within its range between 2 distance values. In this illustration, I drew the volume covered by each bin as a shell around the true location. It is easy to see that the volume of the first bin, which counts the most accurate samples, is a small fraction of the volume of the next bin. So while the samples are denser there, the total count is likely to be smaller. The next bin is bigger, so it will surely have a higher count. At some point, the relative increase in bin volume becomes smaller than the relative decrease in the density of samples, and the counts would start to fall slowly. Here's how deviation histograms for a real study look like. These were published in a recent accuracy assessment paper. Turns out there is actually a mathematical name for such a distribution. It's called a 3D chi distribution. It describes the distributions of length of vectors when each component of the vector is distributed normally. The illustration here shows visually how a 2D chi distribution, which is also called a Rayleigh distribution, looks like, and it's pretty close to what we saw in the previous slide. However, we don't really know that each component of the deviation is distributed normally in a given study, and when it comes to angular deviations, it gets even more complicated. So let me just call it a chi-like asymmetric distribution and make some observations about it. First, unlike with the normal distribution where they're all the same number, here the median is larger than the peak and the mean is larger than the median. Second, while standard deviation is a useful number to have, it doesn't really describe the shape of the curve, so it is not clear how to translate it into a clinically meaningful value such as the 95th percentile. My last observation is that the statistical significance of the results is computed incorrectly in pretty much all the papers I've seen. The t-test being used to compute the p-value of the significance assumes normal distributions of measurements. Okay, well, let me summarize by offering some suggestions about how we could do a better job measuring and comparing clinical navigation accuracy. 1. Please show us the deviations in the study, how they were actually distributed by plotting their histograms. 2. While it's useful for a paper to present the stats for a range of different deviations, when comparing results between papers or systems or studies, let's just pick one type of deviation to represent them all. 3. For that one deviation type we picked, let's use just two statistical numbers, one representing a typical value and the other a more rare bad value. For a typical value with a clear clinical meaning, I suggest that the median is my guy since it is easy to understand. Half the time would be below this value and half the time will be above it. For the bad guy, the maximum comes to mind, but unfortunately maximum is just a single sample and its value depends on how many samples were collected. The more samples for the same system, you'll get a higher maximum. So let's pick the 95th percentile instead. The deviation will be higher in only 1 out of 20 cases. 5, finally, we need to develop a more accurate significance test, one that assumes a 3D chi, not normal distribution. And that's all, folks.